Okay, welcome to Mr. Dahlstrom's pre-AP physics class. We're going to be going over some notes today. This is basically what I would write on the board. We're not going to do any calculations in this video. We're just basically kind of describing the theory and why we're doing what we're doing. So I put little tabs off to the side here of the different parts so that if you're watching this and you want to go back and say, hey, what's a vector, or hey, you know, what are the two ways, or things like that. So I'll try to cover this up with a piece of paper so it doesn't look so much at one time. I'll put this. So today we're talking about vectors and how to describe what a vector is. So if we remember what a vector is as opposed to a scalar, vectors are things like velocity, acceleration, displacement. So it's not only magnitude, how much, it's also which direction. So one important thing about this whole section here is that we need to make sure that our calculators are in degrees. Basically, how you do that if you have a TI-84 is that there should be a mode button, and then I believe it's a mode button, and then you go to you can select degrees or radians. I can go over that with somebody's calculator later. I can make a really short video about that. Anyway, so make sure we're in degrees as opposed to being in radians, because you might be in radians in your pre-calc class when we're in degrees in this class, and vice versa. So I'll always remind you what you need to be in, but degrees is what we need to be in. So let's talk about specifically, not in terms of vectors, but how do we, what drawing vectors and all that. So how do we describe, so this is kind of a lot here, so how do we visually describe or portray a vector? So we've already talked about how we've studied vectors before. Let me adjust my camera here so I can give myself some more room. Okay, we've already described how we've done vectors in terms of calculating, hey, left, right, forward, backward, positive, negative, meaning negative is not less than 0, just means a specific direction. But when we're drawing vectors here and representing vectors visually, we have to draw a vector arrow. And so it seems like I'm breaking down an arrow pretty complicated here, but there's some important parts here. So in this specific arrow, this vector arrow, we have the head. Sometimes this is called the tip, but the head, and then we have the tail, and this is sometimes called tip to tail or head to tail. Also, the length of the arrow shows the magnitude. So it's not something that you're measuring with a ruler, but if I'm trying to show something that is, let's say, 3 meters, if I'm showing 6 meters, it should be double that. Or if I want it going to the left, it should be facing the other direction. So it says direction of arrow represents direction. How surprising. And so that's the one way of describing what a vector arrow is here, okay? So also, the magnitude and direction should be clearly labeled. So I'm going to show you some different ways that you can actually represent, for example, right here, this 5 meters per second. We've talked about in class that we could say 5 meters per second to the right. We could say positive here, because we've seen that at least horizontally positive means to the right. We'd have to be more specific than positive, because positive could also mean up. There's two other ways here. And these may seem more complicated. Why don't we just say 5 meters per second to the right? You'll see just in a second. One way is to use the unit circle, and so don't freak out. We're not doing square root of 3 and square root of 3 over 2 and 1/2 and all of that. You just basically have to know that we're going counterclockwise. That 0 is to the right, 90 is up, 180 is to the left, and 270. And when we get back around here, it goes back to 0. It doesn't go to 360. So I could also express 5 meters per second as my magnitude and 0 degrees. And you say 0 degrees, I know exactly what that would mean. That would mean to the right. The other way, which seems like a more convoluted, even more complex way, is this one right here. I could say that I mean 5 meters per second positive in the x direction and 0 meters per second in the y direction. Now you may say, why in the world am I including that right there? We'll see in a second. So we're actually going to concentrate on these two today because they are the keys to vector addition. Okay, so there are two ways that we can actually express it. So these are good, but they don't really give us an idea of all the different directions. So let's look at these two versions here. So I'll just pull this down there, cover that up at the bottom. So we have two ways of expressing this vector. So let's say that this is a unit circle, 0, 90, 180, 270 as we go around there. So 0, that 0 degrees there. And I have this vector that I'm calling A. Now, one thing I want to express about A, this doesn't mean area. I could say vector B, C, D, vector unicorn, vector star, it doesn't matter. I could say vector V, and it doesn't necessarily always represent velocity. So it's just a generic letter. So vector A here, there's two ways. The first way is called rectangular coordinates, okay? And it may look complicated, but this is all part of making this, making it orderly, because we're going to be doing stuff that are going to cause us to be doing longer problems. So if you think about it, one way you could express this is kind of how you first learn kind of plotting here, is that you could go 3 meters per second to the right and 4 meters per second up, basically creating a right triangle and expressing it. Now this is a different way of expressing it. In your math classes, you might have just said, hey, why don't we just write 3, 4, because we're not really thinking about a point. So, I mean, this is, it may think it's semantics. We're not thinking about what the point is. This is actually some vector. This is some magnitude. We're not describing a point. We're saying how far do we have to go in the x direction, how far do we have to go in the y direction to express that. So this is our format for rectangular coordinates. And it's okay when you're writing this, actually, we'll discuss that later, but we say vector A equals, and you basically say how far you're going in the x direction. So if I was going to the left, I would put a negative in there, but I'm going to the right, so it's positive. 3 meters per second, and then we have this weird symbol right here. Obviously, you understand x and y, but if we look over here, what does that actually mean? It's called hat. So this is called x hat, and that is called y hat. Make sure that you are writing that, and you say, well, why is it so important? Why can't I just put x, and why can't I put y? This is not x, a variable. This is not something that you can substitute in all of this. This is just a way of saying this is 3 meters per second specifically in the x direction. This is 4 meters per second specifically in the y direction. It's not like using y equals mx plus b and x and y mean something different. So this is just a shorthand instead of basically saying 3 meters per second in the x direction. That's what we say. So x hat and y hat, and it's just a little caret thing on top. So really, it is called that. So that's one way of expressing it. But another way of expressing it as well, as you're probably learning in your Algebra 2 and your pre-calc classes, especially with the unit circle, is that we can express this in terms of just the magnitude. So 5 meters per second, and since this is a 3, 4, 5 triangle, this is 60 degrees, just to simplify it. And we could say it's 5 meters per second at 60 degrees. We always measure with respect to that 0 degree line there. So if we have something over here, we measure all the way around on that, and we'll go over that more. So this is, like I said, based on the unit circle, so we can express that. Those are two ways we can do it. They're equally valid. So the question might be, well, I guess, we'll answer in just a second. Why do we even have two ways? That's the second. But let's figure out how we can go back and forth between these, because that's the really key part. This is the beginning of our problems, and this is also the end of our problem. We'll see in a second. So let's say we wanted to go from rectangular and we wanted to express it in terms of polar. You might have an idea here that basically if we wanted to figure out what this 5 was, you might think, hey, maybe we use the Pythagorean theorem. 3 squared plus 4 squared, square root of that is 5. And that is actually how you do that. So going from, oops, let me move my camera down here. Okay. That's how we do that. So v, this is a generic vector, just a generic vector. Okay, it doesn't necessarily mean velocity, although we're expressing velocity for this one. So if I'm going from rectangular to polar, this is the Pythagorean theorem. Okay, I'm taking whatever my vector is in the x direction, and I'm squaring it. So in this case, I would take my vector in the x direction and square it, so 3 squared, plus my vector in the y direction, which in this case would be 4, and I would square it. And if you think about it, that's what you're doing. 3 squared plus 4 squared. Take the square root of that, and you will get 5. Now, this will always be a positive number because we're measuring magnitude. So magnitude doesn't have a direction on it. So there is no plus or minus. This will always be a positive here. And that gives the magnitude. How do we get the angle here? So to get the angle, and I can go over this in more detail in a later video, but just the equation here, we use what is the inverse tangent. Okay, so theta, this 60 degrees here, is the inverse tangent. This is why it's really important you're in degrees and not radians. You take Vy over Vx, so in this case you take the inverse tangent, okay? That's tangent with the -1. It usually is a secondary function on your calculator, depending on your calculator, and you take Vy over Vx, and that is your angle, that is your direction. However, there's something that's very, very important here, and it's this angle correction. We will have to have another video to talk about that. What I mean by that is just a really short discussion here is that your calculator can only give you degrees either in the first or the fourth quadrant here. A real basic idea of why that is that if you mean, let's say you mean negative Vy and positive Vx. Negative Vy would be down, so negative Vy on this would be down. Positive Vx would be this way. So that's the fourth quadrant. But it doesn't know the difference between negative Vy and positive Vx and positive Vy and negative Vx. Positive Vy and negative Vx is over here. So it has some confusion. We have to do some angle corrections. Really simple, just have to memorize some ways to recognize it. But that's how you figure it out. So if you did that, you get 5. And actually for this one, you would need to do an angle correction, and you would get 60 degrees, and that's how you do it. The other way is, what if you have a polar coordinate and you want to go back to rectangular coordinates here? Okay, for this one, really simple here. To find the x component, we take v, and you say, well, what's v? V is whatever our vector is. So v in this case, I know this is a little complicated. V is whatever our magnitude is. So v is the magnitude. Okay. It is the magnitude. Hopefully you can see that. Yep. It is the magnitude. So in this case, it'd be 5. And I'd take 5 cosine whatever my angle. So 5 cosine 60. 5 cosine 60, you'll get 3. And then 5 sine 60, you will get 4. So when we talk about this, let me just check this right here. Yep. Yeah. Okay, so we're going to do some examples here in the next video here. I'm going to take a second here. We're going to go and say, why do we need these two ways of expressing the vectors here? Okay, why do we need the two ways of expressing the vectors? This is the whole point. So I may have to go back and check my calculations here. I think I did it right, but let's hope that I may have. Yeah, we'll check that anyway. So why do we need two ways of expressing vectors here? Okay, this is really an important part. I'll go back and I can correct my mathematics on that, so I apologize there. Why do we need two ways of expressing vectors? But why? It's because of the difference of how we think in the real world versus how we think sort of mathematically. Okay, so here's an example. Let's say we have a map, and this is your start point, and that's your stop point. It says almost everyone would express where they need to travel as magnitude and direction. So they say, hey, I need to travel 2 miles, and I need to do it based on a compass, or I need to do it east, or I need to do it north, so I need it based on there. So there'd be a magnitude and there'd be an angle. Polar is how the world makes sense. Okay, hey, I'm going to go over there. My friend lives that way. Somebody lives that way. However, we could also technically describe it as how far do we have to walk sideways and then walk forward. And you're saying, why would anybody do that? You're walking longer, based on the Pythagorean theorem, you're walking longer than there. It says, however, we can also describe this as moving somewhere to the right or east, and then moving upward or north, and then as rectangular. So once again, why would anybody do that? So here's the kicker. Here's the kind of end here. For that. So because of what's called vector addition and subtraction. So let's look at, you've actually been doing vector addition since you were probably in 1st or 2nd grade when you started adding and subtracting. Just your teachers never told you were actually doing that, but let's look at that. Let's say I have a vector, all of these are completely in one axis, okay? They're either up or down or side to side. So let's say I take 3 to the right plus 1 to the right. Well, on a number line, you would add those, so 3 plus 1, and that would equal a vector of 4. Notice that I tried to express the magnitudes based on the length of the arrow. It doesn't have to be exact, but as long as you can clarify it. Okay, so that's how you get 4. Well, how does subtraction work? You have 3 to the right plus 1 in the negative direction. If you remember, the left here is the negative direction, so 3 minus 1 equals 2. And that's how you do it. That's easy. That's easy for us, right? We're in high school. You should be able to add and subtract. So that's easy. Then when you get into middle school, early high school here, you start looking, well, wait a second, what if I have something 6 to the right and 8 up, and they're perfectly perpendicular here as based on that? Then you learn that you can solve this based on the Pythagorean theorem. I believe this is right. If a 3, 4, 5 triangle is also a 6, 8, 10, You can use that using the Pythagorean theorem. And that is exactly what we did. If I go back just real quick to these equations down here, that's what you did. You would take 6 squared plus 8 squared, square root that, and you get 10. So that's not so bad. But look, they're still perpendicular. They're either completely horizontal or completely vertical. But what if we have an example like this where 6 and 8 are not even in the same up and down direction or even side to side? How do we do it? You can't add 6 plus 8 because 6 plus 8 would mean that they're in a straight line. You can't use the Pythagorean theorem because they're not at a right angle to each other. So how do we solve? It's called vector addition, and future videos will talk about it. A basic, real basic introduction is this is easy. This is really, really easy to do, and so is this for us now. So if we can find some way of, like for example 6, splitting this up into how far do you have to move up, and also 8, how far do you have to move up? If they're in the same direction, you just add them together. And then we have basically a number representing how far we have to go up, okay? And then in this case, how far we have to go to the right, and then how far we have to go to the right. And for this one, we basically have a something representing how far we have to go to the right, and how far we have to go up. And look, we have something that is perpendicular. These two things right here are perpendicular, which means that we can use the Pythagorean theorem to figure out the actual magnitude of that. That's just a really short version. So we want to take something complicated, split it up into what we called our components. We can add everything and subtract everything in the same direction, add everything, subtract everything in the other direction, and we basically, when we do that, we get a value, if I go back here, for something for how far you have to move right or left, how far you have to move up or down. And once again, why are we practicing on our worksheet how to go back and forth? Because we're going to use the Pythagorean theorem and the inverse tangent to figure out what is the polar coordinates. We're trying to figure out what is this magnitude, and also to add to this, if this was a unit circle, what is that angle there? So that's sort of a short version of that. And so I will sign off on this. I need to double check some things, but I will sign off. Hopefully this didn't go too long. There will be a separate video. That's under 20 minutes. There will be a separate video that actually discusses how do we actually do that, how do we convert between those, and that'll go along with the worksheet that'll be on Schoology. So I appreciate you watching. Once again, this has been Mr. Dahlstrom's Pre-AP Physics class there, notes. So I appreciate you. I'll see you next video.